2 of the review. Trig integrals. Sines and cosines, secants and tangents, sums and differences of squares, completing the square maybe. And let's just get into it. So we got this integral here, okay? Sine cubed of x over cosine of x dx, okay? So this is the type of integral that we encountered in section 3.2, part 1, sines and cosines. Yeah, because there's sines and cosines here. But this looks a little different than the one that we saw here, because there's a cosine in the denominator. Well, let's just write it as secant. Yeah, but that doesn't really help us here. Remember with u substitution, right? What I said before, okay? If I have a fraction and there's a function in my denominator, if I try setting u to be my denominator, that's probably going to be the way to go. Okay, well, let's kind of work with that here, okay? If we set u equal to cosine of x, then du is minus sine x dx. Sean, I have a sine cubed over there. Yeah, this is now where we start to use the clever trickery, okay, of section 3.2, okay? Remember, we want to peel away sines or cosines, okay, possibly both. We want to peel them away so that we can force a substitution to appear. Okay? And here's the move, okay? This is probably, honestly, like one of my favorite moves here, okay? We're going to go ahead and peel away one sine from the numerator so that I have 2 left over. Okay. Oh, Sean, sine over cosine, that's tangent. Yes, but does that help me? Not quite. Check this out, okay? In this position, okay, we remember that we have an identity for sine square, right? We have our Pythagorean identity, okay, the starting point. Okay, sine square of x plus cosine square of x equals 1. And I can actually rearrange stuff so that I have sine square equals 1 minus cosine square of x. Neat, huh? Sean, there's a formula in there for sine square x. It's 1/2 of blah, blah, blah. Yeah, but again, does that help us here? No, okay? There are many moves that you can make here, okay? But think about the move that improves your position, okay? Just like in chess, right? All right, so after we make this replacement here, okay, and I realize I should have used the magenta here. So we're going to take the things highlighted in magenta, replace it with the orange there, so I have sine of x times 1 minus cosine square of x dx over cosine of x, and now I'm set. Okay, now I'm set. U equals cosine x, right? Cosine square x right there. So let's go ahead and start replacing. Now, take note here, okay, that I can shuffle the -1 over in the du part to the other side just by dividing by -1. Okay, I'm allowed to do that with the scale factors when I do u substitution. Okay, but nonetheless, okay, what do we have? Well, sine x dx is minus du, okay? 1 minus cosine square x, that's 1 minus u square. Cosine of x is u. But now what? Hey, how do I add and subtract fractions, okay? We have a common denominator. And I have stuff over a common denominator, so I can just go ahead and split, right? We're going to split our plus and minus signs here, okay? And actually, as an intermediate step, okay, just so that I can do some tidy bookkeeping, I'm going to go ahead and move this negative out front, okay? That's a -1, really, okay? It's just going to make my life a little easier and that make this integral a little more easier to look at, okay? You can distribute the minus through if you want, okay? You'll come up with the same result, but I'll go ahead and move that minus sign out, okay? Now, I'm going to go ahead and separate the fractions. So I'll have minus, okay, 1 over u, and then, okay, then I'll have minus, okay, u squared over u is just u. Those are 2 easy integrals. Those are 2 easy integrals, okay? Integrating 1 over u gives me a natural log of absolute value of u minus, okay, u squared over 2. I'll write that as 1/2 u squared plus a constant. Okay, and now what do we do? Well, we're home free. Just replace with what u was. U was cosine x. So everything here is just minus natural log of absolute cosine x. Come on, there we go. Okay, minus 1/2 cosine square x plus a constant. Okay, and if you want, you can multiply the minus through. Okay, a slightly tidier looking answer. Okay, is this. Okay, after you multiply the minus through, so half of cosine square x minus log of absolute cosine x plus a constant. Okay, there we go. So not too bad. Okay, remember, the trick is to peel away sines and cosines, okay? And here, the form of the integrand kind of suggested I needed to do a u substitution with cosine, so I needed a way to force cosines to appear, okay? Tangents and secants. Okay, this one was a little different than our sines and cosines. Okay, now if I were teaching a pre-calculus class, I'd say write everything in terms of sines and cosines, okay? But here, that won't necessarily help you. Okay, in fact, what we should do here is the following. Think about the tangent and secant relationships, okay? I'll give you this here, okay? 1 plus tangent square of x is equal to secant square of x. And that means that tangent square is secant square minus 1, okay? All right, so what do? Well, I have an odd number of secants and tangents, okay? And the idea is that secants and tangents work best together when they're in pairs, okay? So the trick here is I'm going to go ahead and peel away one secant and one tangent from each, okay? So let's write down our integral here. So tangent to the 7th of t, secant cubed t dt. Okay, I'm going to peel away one tangent, one secant. Okay, and I'm going to shove them next to each other. So secant t, tangent t dt. Okay. But how does this help me? Why did I write this? Check this out. The derivative of something is equal to secant times tangent, okay? And the brilliant move here, okay? Well, I guess I could just call it like a great move, okay? The great move here, okay, is that the derivative with respect to t of secant t is equal to secant t times tangent t. But what does that do for us? Well, there's another thing that we have to do, okay? In this position, okay, we're going to also go ahead and use the fact that tangent square is equal to secant square minus 1, okay? But we're going to go ahead and do like a prepping move here, okay? And I'm going to go ahead and copy this, well, okay. We go ahead and copy this down. Okay. I'm going to go ahead and write an equal sign here. And I wonder if I can actually, let's see here, I've never done this before. Okay. Hey, that works. Okay. So what I'm going to do is the following, okay? I'm going to write tangent to the 6th power as tangent squared cubed. Why? Because now I can go ahead and use tangent square equals secant square minus 1, okay? That was the play. Okay, I did that to set up to use one of the identities, okay? That's what you should be doing. You should be thinking ahead, okay? How does this improve my position? So, go ahead and replace tangent square, okay, with secant square t minus 1. That's all to the 3rd power. Let's go ahead and shove the rest of this over, okay? And folks, we are now set up to actually use the substitution, okay? So I kind of suggested it there, right? That the derivative of secant is secant times tangent. So let's go ahead and use it. U is equal to secant t. Du is equal to secant t times tangent t dt. All right? So everything collapses into u squared minus 1 cubed times du. Oh, I just realized we are missing a secant square here. Okay, let's go ahead and fix that. Okay, that's my mistake here. We are missing a secant square. So, secant square here. And now secant square there is u square, then du. Folks, we're basically home free, okay? The only hard part here, I'll highlight this in red. The only hard part is understanding this pattern, okay? How do I do u squared minus 1 cubed? Now, of course, you can multiply it out, right? Do u squared minus 1 square times u squared minus 1, right? You know, use the F word, okay? Not that F word, okay? I'm just going to go ahead and state the results here without proof, okay? But I'll go ahead and write the pattern here. The pattern for a minus b cubed, okay, is a cubed minus 3a squared b plus 3ab squared minus b cubed. Okay, this is from the binomial theorem. Okay, check your college algebra references. Okay, for that. Now you can definitely verify this. Okay, many ways to do it. But we're gonna go ahead and use this for where a is equal to u squared and b is equal to 1. Okay, so getting that out of the way, we have u squared. We'll just shove that out to the front. And now u squared minus 1 cubed, okay, following the binomial formula here, fill in the details, u to the 6th minus 3 u to the 4th plus 3 u squared minus 1, okay? And as you can probably see, this is just a power rule game again, okay? We still have room, that's good, okay? So it's just a power rule game now, so we got to multiply through u to the 8th minus 3u to the 6th plus 3 u to the 4th minus u squared du, and it's just power rule, okay? So we have 1/9 u to the 9th minus 3 over 7 u to the 7 plus 3 over 5 u to the 5 minus 1/3 u cubed plus a constant. And now you just replace the u's with what? With secant. So in the end, we have this. Okay, the only hard part was expanding that cube of a binomial. And that result can be found in any college algebra textbook, but you can also rederive it, okay, just by multiplying it out, okay? Do it in two parts at a time. Secant cubed t plus a constant, okay? All right, so yeah, there was a bit of algebra trickery there, but in the end, it wasn't that bad, okay? Just multiply through, and you've got it. Okay, but the punchline was to remember that secants and tangents come in pairs, okay? When you have odd numbers of both secants and tangents, you want to peel away one of each, okay? Because secants and tangents best work in pairs. All right, we got another trigonometric rule here. Let's take a look here. Yep, there we go. 1 over x squared times the square root of 25 plus x squared, okay? Now, check out section 3.3, okay? We talk about the see and say patterns, all right? I won't go into what they are and what substitutions you should use, but you should be motivated, okay, by the forms of the sums and differences of squares here. Okay, in fact, we're going to use already an identity that we mentioned already. I'll write it down here again. 1 plus tangent square x equals secant square x. And I can multiply through by a square, okay, and I get something here. So how does that help me? Okay, that's motivated, okay? The substitution that we're making here is motivated by this identity, okay? So we see here, okay, we see a sum of squares, okay? So I see x squared plus 25, okay, and here a is equal to 5, okay? So we say x equals 5 tangent theta because dx is 5 secant squared theta d theta. And that is because, okay, if I plug that into my identity, I get some nice stuff, okay? Okay, please watch that video again, okay? It takes practice to understand the patterns and the motivation, okay? But once you see it enough times, you can follow along slowly, okay? you'll be able to get it. So let's go ahead and rewrite the integral. So I have all this stuff here. Okay, 25 plus x squared into square root dx. Okay, now we just go ahead and replace. Okay, and we clean up as we go along. So dx is 5 secant square theta d theta. Okay, x squared, let's just go ahead and write this here. 5 times tangent theta squared. And then square root of 25 plus 5 tangent theta squared. All right, now we're just going to go through and clean up, okay? I won't move the constants out just yet, okay? Let's work on the bottom first. So 5 tangent theta squared. 5 squared is 25. And tangent square is just, well, tangent square, okay? Inside the square roots, okay? Well, we see what 5 tangent square is. We get a 25. Oh, I can factor out the 25. Hey, take a look at what happens, right? You see now why we use that? Because we force a 1 plus tangent square, right? On the top here, 5 secant squared theta d theta, okay? I'm just gonna go ahead and copy and paste because I am lazy. Okay. And now check out what happens in this next cleanup step here, okay? Bit of sleight of hand here, but I'll go ahead and just write it here on the side. Okay, remember that square root is multiplicative, okay? So 25 times 1 plus tangent square theta. Well, 1 plus tangent square is secant square. Okay, and because the square root is multiplicative, I'll take the square root of each factor individually. Square root of 25 is 5. We get a secant theta there. Okay. So that's nice. So, all this to say the following. Erase that. Fix that. I have 5 secant theta here, okay? Now, we're going to go ahead and be very careful about doing the cleanup here, okay? So, here we go. The 5s can drop. One of the secants can drop, okay? And let's just see what I'm left with here, okay? I'm left with, let's just do it here, okay? Well, I have a 1 over 25. I can go ahead and pull that out. Okay, I have secant of theta, d theta, over tangent square theta. So you may be asking yourself, well, that doesn't really look too helpful. Okay, now we just gotta, again, try to think clever, okay? Try to think clever, okay? How can I rewrite this in such a way where things can really help me, okay? Well, when in doubt, write everything in terms of sines and cosines, okay? Secant is 1 over the cosine. And tangent square is sine squared over cosine squared. But it's in the denominator, so it's a reciprocal. We're really thinking cotangents, okay? So cosine square theta over sine square theta. Hey, one of those cosines drops. All right, we're getting somewhere, right? Okay, but how does that help me? Watch. Okay, in this next position, you will find that you have cosine theta over sine square theta. Remember the trick for u substitution, right? If it's in a fraction, take the denominator to be your, take it to be your u. Okay, but in this case, you just want your u here, okay? Let's do it in this color here. U equals sine of theta. Du is equal to cosine theta. D theta. Isn't that clever here? Okay. We still got some space, don't you worry. 1 over 25, okay? We're going to apply that u substitution here, okay? So we got du over u squared. Nice. All right. I know how to integrate that. That's just my power rule, okay? Let's breeze through it. Okay, integrate 1 over u squared. That's minus 1 over u. So I have minus 1 over 25 times 1 over u, plus a constant. And now just unravel the substitutions, okay? U was sine theta. So 1 over 25 times 1 over sine theta plus a constant. Now I could write that as cosecants, and okay, but I like sines, cosines, and tangents, so I'm just going to leave it like this for the moment. Now remember, we're not done because our original problem was an x, okay? And what we need to do, remember, whenever we have an integral of this type, we go ahead and take this thing here, okay, our original substitution, x equals 5 tangent theta. Okay, and we use that to draw a reference triangle, okay? Please watch the right triangle trig refresher, okay? And, of course, the corresponding videos in section 3.3 if you need an idea on how to do this, okay? So we need to go ahead and write this so that we have trig function equals a ratio, just like we're used to. So here we have that the tangent of theta is x over 5. And that tells me how to draw my triangle. Okay? It's my right angle. There's my angle theta. Tangent is opposites over adjacent. Okay? And now I can go ahead and use the Pythagorean theorem to find the missing side. Okay? So we'll just do it off to the side here real quick. X squared plus 5 squared equals c squared. So c squared is equal to x squared plus 25. And so the missing side is the square root of x squared plus 25. Okay. So that's how you draw your reference triangle. Okay, it's just classical right triangle trig. But then what is the sine of theta here? Okay. Well, sine, okay, is opposite over hypotenuse. So in this triangle, it's x over the square root of x squared plus 25. Now I just plug that in, okay? And remember, it's 1 over sine, so I take the reciprocal, okay? So in the end, our antiderivative is, oh boy, let's see, minus square root of x squared over 25 over 25x plus a constant. And we're done with that problem, okay? There was a lot going on here, okay? Some unraveling substitutions that we had to make, okay? 2 substitutions, in fact. First to the tangent, okay? Then a clever u substitution here based on some manipulations. Then, of course, the reference triangle, okay? Please, please, please do yourself a favor and draw the reference triangle. In fact, what you should probably do is as soon as you make the substitution, draw the triangle so all your pieces are there on the table. All right. Okay. Well, we saw integrals like this before. You think we can do a trig substitution? Yeah, but how? We need to complete the square here, okay? So we need to complete the square. Now, here's how we're going to handle this. I'm going to go ahead and write this thing in the square root here, okay? So this thing in the square root, I'm going to go ahead and write it. So 8 plus 2x minus x squared. But I'm going to go ahead and factor out a negative sign, okay, so that the x squared term comes first, okay? It just makes the organization work a little better here, okay? All right, now here's what we're going to do. Remember, for complete the square, okay, we go ahead and look at half the linear coefficient, okay? Take half of the linear coefficient and square it, okay? So negative 2 over 2 squared, well, half of negative 2 is negative 1, squared is 1. So I'm going to go ahead and add 1 and subtract 1 inside those parentheses, okay? That's how we complete the square. Okay, so we're going to do I'll write the plus 1 here first, okay? Then I have minus 1, minus 8. What have I really done? I've just added a fancy 0, okay? Now notice that the first 3 terms factor as x minus 1 square, and I have negative 9 left over. And now, of course, you can go ahead and multiply the negative through, so we get 9 minus x minus 1 square. And folks, now we're ready to go. Let's go ahead and rewrite our integral real quick here. Okay, so this scary looking thing in the denominator, okay, now becomes the following. Dx over the square root of 9 minus x minus 1 squared. All right? What is this really? A squared minus x squared, okay? A squared minus variable squared. Okay? The see and say patterns, all right? We have a squared minus x squared. Here, a is 3. Okay? Now, the idea here, remember, we want to do the sine substitution, okay? But we're going to go ahead and do a compound substitution here. We'll set x minus 1 equal to 3 sine theta. Okay, if this was just 9 minus x squared, then we just do x equals 3 sine theta. But I have that minus 1 there, so I'm going to go ahead and just incorporate it right now into my substitution. Now, I take differentials on both sides, okay? Remember that the derivative of a constant is 0, okay? So dx equals 3 cosine of theta d theta. Okay? Now we just replace just like we've always done, okay? Dx is 3 cosine of theta d theta. And on the bottom, 9 minus, well, x minus 1 is 3 sine of theta square. Okay, and I'll go ahead and do another side calculation here, just like I did in the last problem. Okay, in fact, let me scroll down to give a bit more space here. So the side calculation, okay, remember, 9 minus 3 sine of theta squared. Well, just follow that. 9 minus 9 sine squared theta, okay? Okay, just square both parts of the thing. Now I can factor out a 9. And 1 minus sine squared theta is cosine of theta. Cosine square of theta. Okay, but how does that help us? Well, as soon as I take square roots all the way through, square root of 9 is 3. Square root of cosine square is just cosine. So you see how that all works out? Take a look at this integral. Okay, you're going to be surprised. Look at this. Okay, the integral of 3 cosine theta d theta over, well, all that stuff in the square root collapses to 3 cosine of theta. That's easy. The entire integrand collapses down to 1. Now remember the way we integrate 1, okay? Let's just write that 1 there for completeness. The way that we integrate 1, well, that's just x to the 0, right? Well, in this case, theta to the 0. The function whose derivative is 1 is theta plus a constant. And folks, we're basically done here, okay? Remember, take our original substitution. Okay, so let's write that down again. Okay. But take that. Well, we didn't copy the box there, so that's fine. Okay. We take this. Divide both sides by 3, right? Solve for theta. We don't need no stinking triangle here. Okay. If I take the arc sine of both sides, the inverse sine, okay? This is what I have. So, folks, our antiderivative is inverse sine of x minus 1 over 3 plus a constant. And that's it. That's it. What was the main idea here, okay? It was, well, complete the square, but recognize this as a difference of squares and the see and say patterns, okay? Remember that those see and say patterns are motivated from the trig identities, okay? From the Pythagorean identities. Okay, those are powerful, powerful identities to use, okay? So please, if you're still confused on that, I encourage you, okay? Go back and watch those videos and go back and look at some worked examples, okay? They're all motivated. Try some for yourself, okay? Practice doesn't make perfect, but practice makes permanent. Repetition legitimizes. Repetition legitimizes. part 3, we're going to talk about partial fractions, okay? Lots of algebra there, okay? I'll see you in the next one.